Hi, this is Mr. Waite. Today we're going to be doing the makeup session for the Saturday study session of biochemistry. We're going to look at some grid-in questions. Make sure you have this in front of you. This is the student study guide and the 7 or 8 multiple choice questions we just got finished looking at. That would be in the previous video. And also, we're going to look right now at these grid-in questions. Video after this, we'll be looking at some of the free response questions. Also, make sure you have in front of you an equation sheet that looks like this. It'll be coming in very helpful, especially as we look at this first problem here. Let's go ahead and do that. Math grid-in question number 1. Looking it over gives you some things, and I really like to highlight these even as I'm going along taking a test. It tells me right here, it says my enthalpy, delta H, is 56 kilojoules per mole. Change colors really quickly. It tells me my entropy, delta S, is 178 joules per mole. That's important that those two are different. We'll go back and look at that. Finally, it tells me I'm dealing with a temperature of 25 degrees Celsius. Now, one thing I need to keep in mind here is saying calculate the change in Gibbs free energy. So I'm looking to calculate delta G, but it also tells me it needs to be in kilojoules per mole. Not only that, but it needs to be to the nearest hundredth. That's going to be super important as we get close to the end here. The one thing that doesn't, a couple things don't match. First of all, it needs to be in kilojoules per mole. I'm good with enthalpy up here, but I've got to go back and look at this entropy that says 178 joules per mole. If you're not sure how to go from joules to kilojoules, it's not terribly difficult. I just want to keep in mind that joules are a lot smaller than kilojoules. They can fit inside of a kilojoule, and so when I'm looking at kilojoules, they're going to be a lot smaller. That way I remember I need to move the decimal 1, 2, 3 places to the left. This now becomes 0.178, and that's going to be kilojoules. I'm going to go ahead and cross this one out and remind myself when I'm doing this problem that when I do delta S, I want to do 0.178. The other thing that doesn't exactly fit is our temperature. Unfortunately, we don't use degrees Celsius when we're dealing with math problems, so I need to go back and change this from degrees Celsius to Kelvin. Now, if you're not quite sure how to do that or remember how to do that, I'm going to go back here to my equation sheet, and it tells me right here that to go from temperature in Celsius and change that to Kelvin, I just need to take that Celsius temperature and add 273. So that's what I'd like to do here. Let's go back to this page. I'm going to start out with my temperature, and I know that my temperature in Kelvin needs to be degrees Celsius, which is 25 degrees Celsius, but I need to add 273 to that. When I do that, I get 296. There is no unit for Kelvin. So this is my new temperature value. Cross this one out right here so I don't use that later on. So I have T, I have delta H, I have delta S, and T. With those I can find delta G. This is why it's super important to have this in front of you, is to make sure this is the equation right here. It's telling us delta G is equal to delta H minus T delta S. So when I go back here and I have these marks back here, I can just go ahead and plug in my equation. Let's see, it looks like I lost something here. I went too far, excuse me. There we are. Okay, so the equation from the equation sheet tells us that delta G, Gibbs free energy, is equal to change in enthalpy minus temperature change in entropy. When I do math problems, once I know my units line up, I'm not going to worry about the units anymore, just to make it a little bit more simple. So to solve for delta G, let's put in our enthalpy, which we got from up here, which was 56, minus the temperature, which we just decided up here is 296. Now, if this is a multiplication problem, it's temperature times delta S. So my delta S we said over here was, I'm going to make sure I do parentheses on this one. Actually, let's do parentheses here, and know that this is multiplied by 0.178. Don't forget your order of operations, so I'll want to make sure I multiply first. When I take 296 times 0.178, I get, in parentheses, 52.68. Alright, then I can go ahead and subtract that from 56. Like I said, I'm not going to give the final answer. I'd like you to enter that into play post-it, and I'll want to make sure that you're getting your correct answer. You don't have to worry about units. That's true for the AP test as well. But you do need to go back. When you get your answer, go to the nearest hundredth. So I'm just making up an answer here. If it's 0.25, okay, please don't put that as your answer. But if you did come up with that, make sure you're going to the nearest hundredth spot. Again, if it's 5 and above, give it a shove. That'd make this 0.03. If it's 4 and below, leave it alone. That'd leave it at 0.02. Again, that's not the correct answer. I would like you to actually calculate this out and then type in the correct answer for me. In the meantime, let's go look at this really quickly, the next slide. Just a review. If we're talking about Gibbs free energy, what is that? How does that relate to this stuff? And basically, don't forget this. Most important thing is to remember exergonic. Exergonic, the energy is exiting the system. So you can see, this is trying to show you energies from the reactants to the products. Energy is exiting the system. And because of that, it says energy is going to be released. We're going to actually feel that energy. This is exergonic reactions. What you'll need to definitely remember for the test is that exergonic reactions are spontaneous. They will go forward. Versus the other type of reaction is an endergonic reaction. An endergonic sounds like what it says. We have to put energy into the system. So here's their picture going from reactants to products. We have to add energy to make it go into that. Those are not spontaneous reactions. It is good to remember, though, keep in mind that these are always coupled together. An example of this, where we are putting energy into something, is be something like photosynthesis. Where we are taking energy out of something would be cellular respiration. So, good things to remember. Let's go ahead and look at math grid-in question number 2. And this one's asking us about a stock solution. And it said a student made 4 liters. And the important thing to recognize on this one, let's change color, is that they made this solution. This has happened in the past. And they tell us the molarity or the concentration of this solution as well. It's a sucrose solution. Now they're saying this is what they made. What did they make it from? They made it from a stock solution. That's like what we have back in the chemical rooms. And it says the stock solution had a volume, before the student messed with it, it had a volume of 5 milliliters. So for this one, again, we want to make sure that the units match up correctly. And I always think it's easiest to use the base unit, which in this case is liters. So I want to make sure that my volumes match up. If this is liters, this is milliliters. Milliliters are smaller than liters, so they can fit into a liter. That means I move my decimal to the left. In this case, exactly 3 spots. So 1, 2, 3. So when I do this, this was my original volume. I just want to make sure I get that first. And this is no longer milliliters. This is going to be liters. Okay, what was the original concentration is what this problem is asking us for. Give your answer to the nearest tenth. So again, make sure you have your formula sheet with you. This is the equation we're going to be looking at right here. Excuse me, go back. And it says where we're looking at CI/VI equals CF/VF. If you've taken chemistry, you probably recognize this as M1V1 equals M2V2. That stands for molarity and volume. This is initial, and this is molarity and volume final. In biology, instead of molarity, we refer to things as concentration, and that tells you right down here what everything symbolizes. So this is our concentration initial, concentration final, Or we could have our volume initial, volume final. So let's go back and use this equation, which we just in the problem. So I'm going to go ahead and copy that down. I'm going to say that my C1V1, let's use a different color. So C1, concentration 1, or initial, times volume initial is going to be equal to concentration final times volume final. It might be helpful on these to go back and label the things we're actually talking about right here. So this 4 liters, he said he made this, so this is what the end product was. This is my volume, so I'm going to go ahead and label this one right here. This is my V2, is going to be 4 liters. Make sure you can see that. V2 is 4 liters. Over here, how much of that, what was the original concentration of that it was when it was finally made? So that is going to be my concentration 2, because that's after the student performed this action or this mixture, and this is what they ended up with. So when it says over here, remember this is volume of 0.5 liters. That 0.5 liters, let's just rewrite that down here, is going to be my volume initial. So what is it asking me for here? What was the concentration of that original initial volume of that solution? So what I'm being asked to find here is C1 or Ci. If I would like to get that by itself, I need to isolate that one variable. And so C1, to get it by itself, what do? I need to divide by V1 here. If I do it to one side, I have to do it to the other side too. So this is going to be divided by V1. My new equation looks like C1 is equal to C2 V2 divided by V1. From here, I can just plug and chug. I already said C2 is going to be my 0.1. I'm not going to use units just to keep it simple. We already made sure the units matched up. V2, we said was 4 liters. And my V1, we decided was 0.5. You should be able to solve that from there. Just want to remind you that when you solve for this, you're going to be solving to the nearest tenth. So immediately after, one place after the decimal. I just want to reiterate how important this idea is, even if you get your answer right, but you don't put it to the nearest tenth, it will be counted as wrong. So make sure you're very careful, both as you enter it on this program and when you're taking the actual test. I hope that was helpful for the 2 grid-in math questions for biochemistry. Make sure you get your answers in, and then go ahead and watch the 3rd video. We're going to go ahead and look at the free response questions for biochemistry.